All right, I think we are back, we are online, and today we are going to talk about how we generate plots, how we usually generate plots using Python. Of course, the Python package that we are going to use to generate plots would be Matplotlib, and and we are going to learn quite a few standard tricks along the way today, and quite a few we shall learn how to generate standard plots. Okay, so if we have a data set, or if we have generated some data set, some arrays for example, we might want to look at them and visualize them, right? We sometimes want to see how they really look like, for example, right, to have a visual interpretation. Just having a data having an array containing data often doesn't, give you intuitive ideas about the array, right? So if you have data that you probably have generated or gathered somehow, you can visualize them using Matplotlib. Matplotlib is one of the most interesting, one of the most useful packages apart from NumPy and SciPy in Python, right? This is one of the most used packages in Python. So we're going to talk about that today. And as usual, we shall be using Google Colab for our work. And this file will be shared with you after the end of the session. And again, those who are following me on a computer, I would strongly request you to open a Google Colab session, or if you have Anaconda distribution installed in your computer, open a Jupyter Notebook session and follow along, right? Because again, following along is possibly the best way of learning how to code, right? You have to type in your code. That is how you actually learn the program. Anyway, so we are going to talk about Matplotlib in today's session here. But before we even start discussing today, whatever there is in today's agenda, let's visit this site. And let me paste this in the video description. Right. If you go to this site, it will land you to the Matplotlib gallery, right? So again, so this is the website for Matplotlib. So this is matplotlib.org, and and if you go to examples, it lands you to Matplotlib gallery, right? So here, what you are going to see are samples of different kinds of plots. And again, those who are trying to plot different data in using Python, I would strongly suggest that before you even jump into programming your visualization, I would strongly suggest you go to the Matplotlib gallery and figure out what kind of plot you are looking for, because representing and visualizing data is often a very challenging task, because you can represent the same data in a way that is misleading, right? So there is a popular saying which goes that statistics is nothing but a tool to lie to people. So if you want to lie to people, what can you do? You can use statistics, because that is true, because most of the time what happens, data is somehow misrepresented using certain plots, and those misrepresentation often happens because of the incompetence of the person who is actually plotting the data or representing the data, and sometimes these kind of things happen intentionally. Okay, so you can understand the very importance here. So again, to properly convey the importance of your data, properly convey what your data actually means, you need to look into what kind of plot you are looking for, right? So there are several different kinds of plots. Okay, so here are a few examples. Let me just go through a few of them. Again, these are something called stacked bar charts. Okay, so these are bar charts, like bar chart, right? So on the horizontal axis, you would have certain values or certain names or something. Okay, accordingly, and their values will be values on the y-axis would be vertical axis would be like that. And stacked bar chart. In stacked bar chart, what you have one. So for example, you are comparing two things. For example, under that you would have one bar chart stacked right on top of each other. And there is similarly group bar chart. So for example, if you are comparing two things, this is what you are probably looking for. Let me zoom in a bit. Right. Similarly, you have horizontal bar chart. You have probably seen this kind of bar charts. Okay, right. Now this is again, now this one, it is showing two plots on the same figure. We shall see why how we actually this kind of how this kind of plots are generated. Okay, these are examples of line charts or line plots, for example. So basically, essentially, you are drawing a curve. Okay, here again, here these are statistical plots. So what you are doing, you are plotting the mean along with you are plotting the standard deviation or things like that. Okay, you can do region wise filling in the plot, for example, in this one. Okay, yeah, look at these examples. These are bar charts with fillings, right? You can do different coloring here. Okay, you can put very different colors here. You can make way too many plots in a single one. Okay, so this is called a scatter diagram, and scatter diagram with histograms, for example, here. Okay, we shall see a few of these today. Okay, these are scatter diagrams again. These are again scatter diagrams or scatter plots. And what are these? We shall learn today, right? And these are again different kinds of line plots. Okay, all right. And again, my Matplotlib is able to plot images, for example. Okay, images are nothing but arrays, and we are going to see how we actually draw images using Matplotlib. Okay, examples like that, you're going to see that. And there are several 2D plots like contour plots. Okay, like this kind of contour plots, right? Okay, see, look at this kind of contour plots. You can have contour plots, you can have graph plots like that. So if you're doing graph theory, then you can have those kind of plots. Okay, and I can see, look at the scroll bar here. Oh, you cannot see the scroll bar. I'm only like 25% the way through this page. So there are way too many different kinds of plots that you can generate using Matplotlib, right? If you're doing statistics, probably you have different, very different kinds of plots that you can have. Yeah, look at these. Okay, so like that. Okay, you can have pie charts like this, very different, cool looking pie charts. Okay, you can have scatter pie charts, for example, polar plots you can have, and right, you can properly annotate your graphs, annotate your plots. Okay, so annotation means you are writing something on the plot to make sure that the reader actually understands what they're looking for. Okay, and you can typeset very complicated mathematics within your plots. So that's also the thing. Okay, PyPlot, and PyPlot is one of the libraries that actually helps you to do plotting quite easily. We are going to use the PyPlot library, the PyPlot module inside Matplotlib. Okay, so there are several color and color spaces that you can use. Okay, color schemes that you can use. Okay, all right, and there are several style sheets that are suitable for different purposes. For example, if you are showing your plots on a maybe a news channel, you might want to look for different kinds of different looking plots. For example, if you are using your plot on a research paper, you might want to go for a different look, right? So the look and feel of your graph might be different depending on where you want to present your data. So those are one of the things, right? So again, there are several customization options that are available. You can animate, and you probably have seen animation because I already while teaching you signals and systems, we did quite a few animated plots using Matplotlib, right? You recall that we had sliders and signals were moving around and doing too many things, right? Those kind of animated plots are also available in Python, in Matplotlib, right? All right, and you can of course do 3D plots as well. So yeah, there are several kinds of plots. Again, the very thing that I should tell you first is that whenever you are looking into doing some plotting, looking into data representation, this is part of data representation. If you want to be good at representing your data, you really need to look at the Matplotlib gallery, because there you shall find you might probably find a certain representation that would probably suit you better. than the one you might have already in your mind. So yeah, so there are 3D plots, fantastic looking 3D plots, for example. So again, we are going to look through quite a few of these. Okay, of these things. All right. All right. Okay, and you can have logarithmic axes. No one is stopping you from using logarithmic axes. And of course, we do use logarithmic axes, right? Because we are electrical engineers. Okay. For example, if you're doing MRI scan or things like that, you can plot them as well. You can do 3D voxel plots. For example, 3D pixel is called a voxel. You can do voxel plots like that, right? So there are literally, I mean, hundreds of different kinds of plots that Matplotlib would support, essentially. All right. Okay. So we have just looked through the different available plotting types. Okay. All right. But the fundamental thing that stands behind everything is NumPy once again, because again I told you NumPy provides you a fantastic way of manipulating arrays, right? Very fast and useful ways of manipulating arrays, right? So if you are talking about arrays, if you want to store different data, okay, if you want to read different data, in any of this situation, what you would do, you would create a NumPy array, because NumPy arrays are pretty fast. Okay, and I'm going to show you how you can actually import data from a file and plot that. Okay, we're going to look at that as well. This Matplotlib to some extent can also let you do real-time plotting. So real-time plotting means something is happening in real time and a certain plot is being generated as the event is happening. Okay, so those kind of plots are also available inside Matplotlib. All right, but little bit of history is in order. So Matplotlib was created back in late 90s and early 2000s by a scientist named John Hunter, and he used to work with MATLAB. Okay, he used to work with MATLAB, and he was a neuroscientist, and he was a very famous neuroscientist back in his day, and he used to do his plotting using MATLAB. MATLAB is a pretty famous software, but it's a proprietary closed source software, and it's a extremely costly software, right? So if you're opening your own company, maybe you're an entrepreneur and you want to open your own company, MATLAB might not be a good choice for you because it costs a lot of money. All right, and it's also proprietary. Python is open source, free software, right? Essentially. So, so he was working with MATLAB, and he wasn't really satisfied with the quality of the plots generated by MATLAB. And really, honestly speaking, the quality of the plots generated by MATLAB did not improve up until 2014. So, right, I did learn MATLAB before that, and back in those days, the quality of the plots generated in MATLAB was really poor, to say the least. Right, was not up to par. So then after 2014, things become much better, right? But he figured out that, I mean, MATLAB wasn't sufficient for him. So what he did instead. So that is what, as the saying goes, if you don't like something, don't complain. Change it. You are not a tree, right? So he did not complain that okay, MATLAB is bad or things like that. What he did instead, he instead created his own library for doing plotting. Okay, for plotting signals. Again, for example, right? So he was a neuroscientist, and his work. So Matplotlib is essentially the result of his work. So he was the primary author of Matplotlib, and he was the primary author of Matplotlib until 2012. Okay, until he died of cancer, essentially. So yes, he was one of the most prolific figures in the entire Python community. Right. So this is pretty much, he died 8 years ago, but this is his legacy. Okay, legacy of John Hunter. Right, and I have listened to quite a few of his lectures. Those were like awesome lectures, really. Okay. Anyway, so now histories are over. Let's jump into actual programming, right? So, right, let's create a new notebook. Again, I am opening collab.research.google.com. Again, I would strongly suggest you actually follow along by typing your code. Again, the very reason why I'm teaching you Python is because the job the job prospects nowadays are changing rapidly, right? And Python is one of the, I told you this in the very first class on Python, right? And I mean, learning Python is pretty much becoming an essential skill. People might forgive you even if you don't understand C programming. People might still forgive you if you don't understand mathematics, don't understand complicated mathematics. People would forgive you if you don't understand control system engineering, right? But people won't forgive you if you don't understand how to program in Python, probably. So it is becoming really important on the present perspective. So let's create a new notebook, right? So I have opened Google Colab here, and let's start. Let it start. All right, so I'm calling it. All right. Of course, the name Matplotlib came from the fact that John Hunter was working on MATLAB, and he wanted to create a plotting library reminiscent to how plotting is done in MATLAB. So Matplotlib literally stands for MATLAB-like plotting library or matrix plotting library, things like that. So essentially, Mat actually came from MATLAB, sort of. Right. So again, if any one of you is somehow familiar with MATLAB, you would see that the plotting syntax in Python, if you're using Matplotlib, is very similar to that in MATLAB. Or at least it used to be for the most part. MATLAB has changed significantly over time, but the fundamentals have remained the same. Alright, again I'm making a 150% zoom. Alright, so again we are going to learn the actual proper way of doing plotting in Matplotlib, and also then we are going to talk about the easier way of doing plotting in Matplotlib, right? Again, the libraries that we would need at the very least is NumPy. So we are importing NumPy as np. So of course, since the fundamental building block of Matplotlib is again arrays, right? And arrays are provided by NumPy, so we are importing NumPy. So again, NumPy is kind of a dependency of Matplotlib. You can do plotting without NumPy, but that would be pretty inefficient. Okay, you can plot lists, but Python lists are pretty inefficient as themselves. And as such, if you want to install Matplotlib, Matplotlib won't work without NumPy. So NumPy is kind of a dependency of Matplotlib. So if you want to install Matplotlib, you have to also install NumPy. That's a dependency again. And again, if you have installed Anaconda Python distribution, then you already have all of this. You don't have to worry about installing something. If you are using Google Colab also, you also have everything. Excuse me. Hold on for a second. All right, so we have imported NumPy, right? Then we have to also import Matplotlib, and you have probably seen this kind of imports. And now we are not directly importing Matplotlib. So actually, from Matplotlib, inside Matplotlib is the whole package, right? And from Matplotlib, actually we are importing the PyLab module. And now PyLab, of course, again the name is reminiscent to the fact that actually Matplotlib was created as a replacement for the plotting libraries in MATLAB, right? So PyLab is pretty much like MATLAB for Python, so PyLab. Okay. So again, this is one of the standard imports that we people do, right? So we import the PyLab module from inside Matplotlib as PLT. So PLT is essentially pointing to the PyLab module inside Matplotlib. So PyLab module provides you some helper functions that will help you to actually plot things in an easier fashion. Okay, like those in MATLAB. Again, if you are not familiar with MATLAB, you don't have to be. And as usual, if you have any query during the session, please feel free to ask. And just one more thing I should tell you, there are quite a few other very interesting and powerful packages, plotting packages in Python. One of them is bokeh, one of them is Dusk, one of them is Plotly. So these are standard important packages also. These packages are also used for plotting. So again, Matplotlib is the most used package for plotting. So these are the two standard imports that we people do. Right? So we would import NumPy and we would use import Pylab, matplotlib.pylab as PLT. So again, the naming scheme is pretty much, you could call it, so this is an alias, right? NP is an alias. You could call it anything, but NP is a standard alias and PLT is also a standard alias. So if somebody sees PLT, it is understood that it is referring to matplotlib.pylab. Or rather, I would say pyplot. So I'm not importing Pylab, let's import pyplot. So I'm only importing the plotting library as PLT. Let me just rerun that. Okay. So instead of just Pylab, let's import. Okay. So these are the two standard imports we can actually do. Right? So let's do a very simple thing. Let's create an array. Right? Let's create an array. Let's create an array. So T. Fine. What is T? So T maybe is time. All right. T is maybe time. So okay. Time would be linear space, for example. So np dot linspace. So I want to start my time from 0 second. I want to stop my time at maybe when do I want my time to stop? Here maybe like maybe 0.1 second. All right. So right. So time starts at 0 second, ends at 0.1 second, and how many points do I want to take in that array? Maybe I want to take 100 points. All right. So just to show what kind of array I have created. So I have created an one-dimensional array that starts at 0 and ends at 0.1. And how many points do I have? I have 100 points, right? So the spacing between the points is like about 0.001, something like that. So essentially we have created a time array for holding our time here, for example, and starting from 0, ending at 0.1, and the number of points is 100, right? Again, you have seen this, right? So now let's create a voltage signal and let's make it a sine wave. So NumPy, so from NumPy we're importing sine. So let's make it a sine wave and say, of course, we have 50 hertz signals, right? So 50 hertz. So you already know that how to write 50 hertz. So 2 pi, and how do I write pi? Pi is also being imported from NumPy. So np.pi. So look at this very carefully. So what happens is, so we have a 50 hertz sine wave. Look very carefully. So this is 2 pi f is 50, for example. In Indian power system, the frequency of our alternating current is 50 hertz. So this is a 50 hertz sine wave, right? And let's plot this. So I can, from the plotting library, I can call the plot function and we can make a t versus p plot, v plot. So time versus voltage plot here. Let's do that. Fantastic. So we have a very simple plot, right? All right. So here in this axis, in the horizontal axis, we have time, and in the vertical axis, we have the amplitude, right? We have the amplitude. So that's also fine, right? Is there any difficulty understanding this? I don't think so, right? But the thing is, notice very carefully, I mean, whether I don't know how the YouTube compression is working. This plot is looking kind of jagged, right? So what if I take less number of points? Maybe I want to take 50 points here and then I plot. If I do that, look at the plot, what happened? In this entire array, I have only 50 points. So the spacing between the points in the time axis is not sufficient for us. And because of that, what is happening is the plot is not smooth. So if you want to have a smoother plot, you would want more number of points, so maybe 1000 points. So now I have taken 1000 points within that gap. So now I have a nice looking sine wave. Fantastic. Nice. No issues. Let's call this instead, let's call this now of course it's a plot nice, but I have to tell people that this axis is representing time, right? Because otherwise if I just give somebody this plot, what is it? Nobody knows really. So this must represent time. So I have to tell people that okay, the horizontal axis is representing time, and time in seconds. So I would say plt dot x label. So of course x label stands for label for the x-axis, and it would take a string, and I'm saying time in seconds. Now if I plot this, see what happens. Now in the horizontal axis I see it says that time, right? So now if somebody gets this plot, it will be understood that okay, I have time in the horizontal axis. Okay, now that's not sufficient. We still also want to do want to write something here in the vertical axis as well, right? So we would say voltage probably plt, and for that it will be y label, and say I would say amplitude in volt, for example. Now if I run this and forget this, okay, and forget this text, whatever, this is a caveat of Google Colab, also Jupyter Notebook. Okay, fine. So look at this one. So time is in this axis and amplitude in voltage in this axis. So you have this. Now what else is missing? It's a plot, right? You probably want an axis, right? You probably want a grid, right? So proper grid lines. So for that, you want to call the grid function from the, again, PLT module, right? So now if you do that, look, we have a nice looking grid. Okay, so proper uniformly spaced grid, linear grid, that is actually accompanying our plot. So we have nice and clear plots like this. So we have time in this axis and we have amplitude in this axis. We have completed a single simple line plot. We have created an array, and from that we have created a plot. All right, fine. Now what if I want to plot something else on top of this one? Maybe this is just a single sine wave. This is one of them. Maybe there is another one I want to plot on top of it. Okay, so let's create so v1, right? This one is v1, right? Maybe I want to plot another one, right? Maybe there is v2. Yes, we can modify the grid. There are way too many things that you can do actually. All right, we are going to show some of these things to you, and then I shall leave it to you to find it out later on, kind of. Okay, let's create another voltage signal, same, another sine wave, so of the same frequency. So to np dot pi 50, and of course start t, and let's add a phase angle. This help menu is ruining me. Let me see. How can I stop the help menu? I don't know. Hold on a second. Notebook settings. Is there any? No. Hold on. Okay, we shall see that later on. And let's create a phase angle, for example, right? Let's create a phase angle of, say, for example, 120 degrees. And of course, this sine only takes radians, so 120 degree would be something like 2 star pi by 3. So that's 2 pi by 3, right? So we have another sign. Fantastic, right? So this is the same sine wave but phase shifted by 120 degrees, right? Now let's create another sine wave. Let's consider that to be another voltage, and now let's phase shift this by 240 degrees. So now I have three sine waves with the same amplitude but a certain phase shift among them. Now what if I want to plot them? So after creating V2, what if I want to plot them? I can simply say plot T comma V2. So that would result into a plot like that. After creating V3, and again plot is coming from the PLT module. What? Okay. And this comes from PLT module, and again I can say plot and then T comma V3. All right, let's run this. So what I essentially have, I kind of have a representation of the T phase sinusoidal behavior. So we have kind of a plot for three sinusoids, phase 120 degrees apart. Okay. Those are kind of the three phases. All right. Nice. So we have generated three plots all together, all at the same time, or the same figure, right? Now here, since we are not modifying anything about the plot, I mean doing the plotting in this way might not be a good idea often. What happens is, I mean, we are kind of wasting our time here. What we could do instead, we could create everything and then plot everything. So this is what we usually do. We generate all the arrays that we need. So these are all the signals and whatever. Okay, this is time, this is the first voltage signal, the second voltage signal, the third voltage signal, and then we go for plotting, right? So this is what we usually do. We usually generate everything first and then plot. Okay, this would result into the same plot, but we can do even better. Instead of plotting them separately, instead of doing these, what I can do, I can plot all of them at the same time. So this was T versus V1, then I can write T versus V2, then I can write T versus V3. Okay, under these scenarios, if the independent axis is the same, so for all of these plots, T versus V1, T versus V2 and T versus V3, the independent axis is time, right? So if the independent axes are the same for all of these plots, then we can combine them like this. So, and as such, we shall get the same plot. Now the code is pretty compact here. Okay, so this is again always recommended that you generate your data first, okay, or retrieve your data first and then do the plotting. So again, we keep the plotting as a separate thing for itself. So again, this is one of the basic plots that you can actually generate. All right, nice. I think there isn't any complicated issue about this. And if you are if you want to ask some special questions about this, please ask. If you are trying to find out something about the plot or something, okay, please ask. Okay, let's delete this. All right, so we have kind of superimposed multiple plots in here. Nice. So we imported our modules, we have generated our nice plots here. All right, fantastic. Now let's jump into a different kind of plot. Okay, now you people have, if you recall, we were talking about random numbers, right? We were talking about random numbers. Let's deal with random numbers a little bit. Okay, so let's say x was np dot random dot rand. So random numbers, right? From NumPy, someone is asking something. Yes, if the independent axes are different, then you probably want to plot them separately. And maybe if the independent axes are different, then maybe you don't even want to superimpose the plots, right? Do you understand my point? So if they are not dependent on the same axis, same independent axis, then you do not You are not supposed to probably plot them in the same plot. And how did the color change? The color automatically changed. And I will teach you how to modify the color as per what you want. Okay, but the color change automatically. Okay, it understands that you are superimposing plots, and of course it won't trouble you by making the plots of the same with the same colors, right? So it generated the color automatically, change the colors automatically. So now let's create random numbers. Okay, let's create random numbers. Let's say let me create 50 random numbers. So this is going to give me 50 random numbers. Again, random numbers drawn from a uniform distribution between 0 and 1. So we talked about this. Right? Let's create another set of random numbers. So that's another 50 random numbers, right? Fantastic. Now let's plot them. Let's plot x. Let's plot x. Okay. If I just plot x, what am I plotting? I'm just plotting values. Someone is asking something. Can we make specify? Yes, absolutely. Someone is looking for. So someone is asking, can we specify which graph is which? Yes, absolutely we can. That's called legends, and we are going to talk about legends. Okay, we are going to talk about legends. Definitely, we are going to talk about legends. Don't worry. We are going to talk about legends and subplots and everything. Now here, look at this one. So we have just done a plot on x. So essentially now in the horizontal axis, what we essentially have are the indices. So this array x, if I just print the array x, this array x would have 50 points in it, right? This array x would have 50 elements in it, starting from index 0 and index 49. So here in the horizontal axis, we have index 0 to index 49. And in the vertical axis, we have the data. So again, it's a random signal, so pretty much it will look like a noise, right? So it is pretty much like a noise, random noise. Okay. So uniform noise, for example. Noise do not often look like this. Yeah. Hold on for a second. Sorry for that. And okay, fine. We have that. Okay, fantastic. So before we just jump further, let's do a plot like this. A plot. Let me say plot. Plt.plot. Let me just write down something like this. Let me say I'm passing in a list. I'm saying 1 comma say I'm passing in a list. This is 1 and say this is 2. Okay, let's see what happens. Okay, nothing. What? I just passed in 2 values. What happened? I have 1 and I have 2. Something like say 1, maybe something like that. Okay, what happened? Nothing really happened. All right. Nothing really happened because what I just did, I did plot a single point. So and the coordinate was 1 comma 2. So here the coordinate was 1 comma 2. And now let me just do this kind of thing. So for example, so now essentially we are plotting 2 points. Look carefully. So essentially what we are doing, we are plotting 2 points and the coordinates are 1 comma 2 and 3 comma 10. So 1 comma 2 and 3 comma 10, right? 1 comma 2, 3 comma 10. So points from this list will become the abscissa, so will become the points on the horizontal axis, and points from this list will become points on the vertical axis. That is how we generate plots, right? So again, recall in this one, so the first thing that we passed in was the array for the horizontal axis, right? So the same thing we are doing. Here we are passing in the array for the horizontal axis here, and this is the array for the vertical axis. Essentially, these are just coordinate points, right? What if instead of this kind of plot, what if I want to make, for example, what if I want to just make the points be represented by points like that? So instead of this line, what if I want dots or other circles in their place? So what I would do, I would, after passing the lists or the arrays, I would just pass in a marker. This is a marker style. Okay, if I pass in this marker, what happens? is that instead of those, I just get 2 points. Look carefully. I have got 1 point at coordinate 1, 2. So that's 1, 2. And I got another point at coordinate 3, 10. Right? Just like that. That's very easy to understand, I think. So now let's pass in x, y. Right? And the plot would look pretty bad. I mean, it won't make any sense. Okay. But what happened is, it took all the points from this array, from the array of x, and considered them to be the x coordinates, and then it took all the points from the y array and it considered them to be the y coordinates, and joined everything with lines like that, right? So this is kind of a bad looking plot. What if I want to plot them as points? So what I would do, I would rather plot them as circles, small circles. So if I do this after this one, so I am passing in this marker. So now look carefully what happens. So now we have just made a plot where we only have points. So essentially we have 50 random points in the random points denoting the horizontal axis, 50 random points denoting the vertical axis. Somebody is saying why are x and y are the same plot. See here, if I am plotting this is x is being considered the independent axis and y is being considered the dependent axis. So these two are belonging to the same plot. Yes, these two, x, y, is a single plot. It's a single signal, for example, right? It's a single plot. That's why they are all having the same colors. All right, that is why they are having the same colors. I think that's understandable, right? All right. So now let's increase the number of points. Instead of these, let's make them 500 by 500. And then now let's look at the plot. Wow. So I essentially have 500 points where x coordinates are determined by this axis and the y coordinates are determined by this axis. But again, this is just a single plot. This is not multiple plots. This is just a single plot. That is why they are having the same colors, right? That is why they have the same colors. All right. So something that is understood, right? Okay. I don't think it's difficult to understand, right? All right. So we have generated. So now again, look very carefully. We said we are drawing numbers from a uniform distribution, right? Uniform distribution. Again, look very carefully. Uniform distribution. That's fantastic. Now, of course, uniform distribution means I'm drawing all numbers uniformly from 0 and 1, from a bound of 0 and 1, right? So we are drawing random points between 0 and 1 uniformly. Now imagine this is a board like that and we are drawing random numbers. And how we are drawing random numbers? For example, we are blindfolded and we are just throwing darts on a board, right? And it is randomly hitting every place. So imagine a situation where every point is equally likely to be hit. So see, the distribution kind of looks uniform. Okay, and we're going to talk about how to plot distributions like that, right? Let's increase the number of points, make them 1000 by 1000. Oh, sorry, I did make them 100 by 100, unfortunately. Let's make them 1000 by 1000. So now I have 1000 number of points. See, they are uniformly pulled from the uniform distribution, right? So this entire board is being filled in uniformly. So the random numbers are actually uniformly filling in the axis like that, filling in the plot uniformly, right? All right. So again, so we have just seen, you people have just seen a marker style and to plot arrays like that. Again, if you have any difficulty understanding this, feel free to ask. Right? So now let's create a very simple array once again, and let me show you different marker styles. Let's create a time array, and this time we are going to make it simpler. So now say an np dot linspace. So from 0 to 10, and we are going to consider 1000, say 100 points. We're going to say consider 100 points, and say x would be np dot, say for example sine wave. So actually just let's take sine t. Okay. All right. Let's make a 1 radian per second sine wave, and let's plot this. Okay, very simple plot. Again, we have already done that. Okay, I have to say plt dot plot. All right, that's a simple plot. Okay, now what if after writing this, I make this? Okay, look carefully. The plot was generated, but instead of drawing a smooth curve along them, it is showing circles at each point on the curve. So let's make different plots with this. So this was the first one I said. So just to keep a documentation of this. Now I shall be drawing a different plot here. So here, if I just pass in this one, so now see what happened. Now we have passed in a marker style, so it is now showing circles like that. But what if I pass in another marker style? Maybe I don't know how nicely it is being compressed by YouTube. I really don't know. But let's say I'm writing S. So what happens? The marker has been changed to squares. Okay. What if I pass in something like a dot? Okay. So then a marker will become very small dots. Okay, these are not circles. These are not as big as the circles, but yeah, smaller than them, right? All right. So we're just playing with different marker styles here, right? So we know what circle is, right? Now, right. Now look at this one. What if I put a dash? Okay. So it will indicate that nothing. The same basic plot that we have already had, right? So, and of course everything has been joined together by the smooth curves, right? So essentially what we have just seen, that dash essentially means that of course the points are being joined by a smooth curve, right? But what if I say dash dash? Now we are looking for different curve styles now. Now again, now it's a dashed plot. Often what happens, you don't always have the luxury of plotting everything in color, right? Often what happens is, maybe you want to print something in grayscale, right? Print something using a grayscale printer, black and white printer, a printer which is not in color, does not have color, right? Under those, if you make plots of different colors, then it won't make any sense if you print them in black and white, right? If you print them in a grayscale printer, what happens is those plots won't make any sense, right? So those color plots won't make any sense. So having different style of curves is nice in case you want to print everything in grayscale, like black and white, right? So that is why these things are there. But again, if you have the luxury of using different colors, then this is always recommended, that instead of using different styles of curves, you instead use different colors for the curves, because different changes in colors immediately register to human eyes. But in case you are looking for printing them in black and white especially, in that case it is always recommended that you make sure to have different markers. So, and with that said, often we people, what we do, we use different colors with different markers and line styles. Okay, so that if somebody is looking that on a computer screen, for example, where everything is colorful, it immediately registers with different colors to human eyes. But if somebody is printing those plots, or maybe printing those papers on a black and white, using a black and white printer, then also everything is retained, the information is retained, right? The plots would still look different because they are having different line styles, not just different colors. So in practical use, we always use different colors and different styles. Again, that's true if we are superimposing different plots. And again, we are going to show what plot is looking and what plot is what. We're going to represent that properly as well. Now, right there. So let's let me show you another line style. For example, say for example, I have another line style. Say, so what is this? Now this is combining a dash with a dot. So this will be a dash dot plot. Look at the curve here. So it's a long dash and then a dot, long dash and a dot. You probably have drawn this kind of curves in your engineering drawing classes, maybe. Okay, again, that's a possibility, right? But this might give you a hint that, remember what this dot was. This dot was essentially plotting dots, right? So this was the marker style and this was the line style. So we are joining a curve here. So we can combine marker styles and line styles. Okay, so maybe I want markers to be represented with circles, and then I also want them to be joined. Just as a reference, if I just say O here, what happens? I only get the markers, right? But if I say O dash, then I also get the curve, smoothly joined one. So is it visible? So now everything has been joined. It will be better visible if I say dot dash. So I would get those dots, and also I would get a smooth curve joining them. Right? So there are 3 types of styles, rather 4 types of styles here. Okay, you can change how you can change the color. I'm going to show you how do you change the color. You can change the marker style, you can change the curve style, and you can change along with that. So you can change the color, you can change the marker style, you can change the line style. Yeah, like that, all 3 of them. Yeah, you can also say a star here, then it will generate, it will plot stars here, for example, stars. And then of course this is denoting a curve joining them. So yeah, like that. Sorry. So only stars, so star and then a smooth curve joining them. Then if I say star dash dash, that would actually give me a dashed line joining those stars. Okay, so you can combine marker styles and line styles. Okay. Oh, and you have also curve width, so you can vary the width, how thick the plot is, you can vary that. You can change the color, you can change the width, you can change the marker style, you can change the line style. So there are 4 different things that you can do about your plots. All right, now let's talk about colors. What if you want this plot to be in black? Okay, what if you want this plot to be in red? Let's say so of course the syntax is just you pass in this string, or rather this character R, and now it will plot everything in red. That will be a red one. So now you can manually vary your color. I think you can understand, right? So here maybe I want this plot to be in pretty bad looking blue. Maybe that's a blue one. All right, all right. Of course, if I want them to be in green, yeah, let's say G, green. And some of you already know that color values are essentially hexadecimal values of 6-digit hexadecimal values. You can pass in those 6-digit hexadecimal values, okay, or pass in the color arrays denoting different values of R, G, and B. You can get exactly the color you want, and that is something I personally do. Whenever I do plot, I have a particular theme of mine. And there, I personally change the color according to the way I want it to be. Okay, all right. So again, so that's again nice. Right, good. Now, what if I want a black plot? Of course, B is reserved for blue, so black is called K. I don't know why it is called K. Maybe it's color. That is why. Right. So that's a black one. Nice. Good. So we have talked about colors. We have talked about marker styles. We have talked about line styles. Let's talk about combining them. So what if I want the plot to be in black, and what if I want dashed lines? So black dash lines, so K dash dash, it will be black dash lines, right? Okay, maybe I just want to combine, so I want to make them black and circles. That will be K O, right? Black circles. All right. Yeah, actually, the funny thing that programming language, I mean, most computer, rather software terminology and computer related terminology is kind of racist, and this recently made news headlines, and things have been changed. Okay, we have this, what, so for example, you have studied flip-flops, right? You have the terminology master slave. So those so again, slavery is really bad, has been eliminated from the world, but still you have the word master slave, right? Okay, so if I want to block something and if you want to So if I want to block something, we call everything that has to be blocked, we put them in a list called a black list. And if I want to pass something, we call that a white list. Again, discrimination between black and white. Yeah. Those things are there. So software terminology is pretty racist by default. Okay. Yes, I just changed the marker style along with color, right? Moments here, I have changed the marker style with color. So I have made it, someone is asking, can I change marker along with color simultaneously? Yes, I did change the marker along with the color, right? So by default it would have been blue or something like that. I just changed the marker style along with the color. So I have made it a black one. Sorry, I made it a black one. So that's the color change, and marker has been changed to circle. I can combine all three here, not just all three. You'll see. So I can make this black, maybe. Okay, maybe let's make it this red, and maybe I shall use, I don't know, maybe star. So red star, and I shall join everything. So it will be a plot in red. There will be star markers, and there will be a smooth curve joining all the points. So red one, stars being used as markers, and a smooth curve joining all of them. The thing is not just that, we can also vary how thick the line is, right? Yeah, things are changing. Someone is saying things don't change, but things are changing really. So instead of saying black list and white list, the words have been rephrased as block list and allow list. And again, instead of saying master and slave, words have been changed to primary and secondary. Okay, those are pretty nice term, right? Electrical engineering is kind of safe from that. We don't really use many racist terms really, but in software engineering we have lots of racist terms really. All right, so now what if I want to change the line width? So of course there is a simple syntax of, now we can say the line width to be equal to 2, for example. By default it's 1. Now I don't know whether it is visible or not, but the line is slightly thicker here. I can make the line width 5. What if I do that? See, the line is much thicker. All right. Now we can combine everything. Okay, let's make a black plot. Okay, black plot with dashed lines and make them as thick as 5 point, right? So this is denoting that I want the plot to be in black. This is denoting that I want dashed lines, and this is denoting that line width is 5. Just a point to note though, if you recall Python functions, our class on Python functions, you know these are positional arguments. Time t is a positional argument. This is also a positional argument. This is also a positional argument, but this is a keyword argument, if you recall. So again, the Python terminology is that positional arguments cannot follow keyword argument. So if I somehow pass in this one after saying line width equal to something, because again this is a named argument, right? Then it will throw up error, and which exactly says what the problem is. It says positional argument follows keyword argument. That cannot happen. Once you have done all the positional arguments, then you can only write keyword arguments. So just keep that in mind. You can, this is the correct syntax, so you can actually do this one, right? So the moment you say something equal to something inside a function, so this is the function call, right? Inside a function, if you say something equal to something, so that will be a keyword argument. Okay, and these are all positional arguments. So the point is, once you have keyword arguments, the notion of position is pretty much violated. So you cannot have positional arguments like that. All right, nice. Right? All right, let's now go back to our original plot, right? Let's bring this one back. Where was it? Let's bring this one back. All right, let's bring this one back. And now, say let's plot them one by one. So that was the sine wave, pure sine wave, fine, right? And maybe I want to write something after this, so I want to label them. So I'm saying label equal to, say I'm saying sine, what should I say, 2 pi okay, instead of saying all these things, let's just say all right, let's say that nothing will happen now. Of course nothing will happen, nothing did happen because yeah, I just labeled this plot, right? So in order for the labels to appear, so I would say plt dot legend, like a legend. Say for example, if I say plt dot legend, now it says this is the first phase. Can you see this? Okay, so whatever label I gave it, now it is saying this blue one is the first phase. Okay, let's now plot a next one, and again, if you are just doing labels, then plotting them differently is nice, easier to remember. So this will be the second phase. Now if I plot them with the proper label here, see, the label indicates that the blue one is the first phase and the orange one is the second phase. And if I plot the next one, okay, I can say this one, so this will be the second. All right, so V3 is the third phase. So now we have these three phases, and this is called a legend. Okay, plot legend, right? So we have, so essentially what we have done, we have labeled our plot, and then after plotting we have called the function legend from the PLT module, right? We have from the PLT module we have called the plot function, and with that we have this plot, right? This legends right here, right? So now they are pretty distinct. Now what if I am printing them in black and white paper, right? I mean with using a black and white printer, of course nothing will be understandable because these colors will pretty much disappear, right? Our eyes won't be able to discern them, right? So with that said, so what we can do, we can now change them to different markers. So again, this is a keyword argument, label is a keyword argument, so we're writing label equal to, then if I want to use markers, we have to do before that. So I want to use markers like, maybe I want to write maybe I want to put markers like star and then join them with a curve here, and here I want a marker like circle, and then I want to join them. You would see a problem with this. You would see a problem with this kind of plot. You will see. And then maybe with the other one, maybe I want a square, maybe, or maybe a pentagon, whatever, a square and maybe a smooth curve joining them. You would see there is a problem with this kind of a plot. Okay, what just happened? Everything looks awful, right? So what happened? What happened is that the points are too close by, so they are not sufficiently far apart for these markers to be properly visible, because within this small plot I have created 1000 points, and since within this small plot we have 1000 points, the points are not far apart so that the markers are properly visible, right? So now we have a dilemma. The problem is that we have to either make the plot larger or we have to reduce the number of points. Let's go with the second option. Let's reduce the number of points. So instead of 1000 points, let's make 50 points. Now the plots are looking pretty bad because all the edges are jagged. Okay, really bad. So now here comes your pretty engineering skill. So instead of plotting for 1 second, plotting up to 1 second, it's a 50 Hz sinusoid. So within 1 second, there will be like how many? 5 full cycles of the sine waves within 0.1 second. So instead of doing that, let's reduce this. So let's make this plot up to 0.05 seconds. Nice. All right. So we are doing that. Maybe I want to increase the number of points a little bit. So let's make this 100. Let's see what happens. Nice. Now look at the legends. Look at the legends. Now, of course, the green one is having this. Again, I did not choose the colors myself. The colors has been chosen by Python itself. Okay. So this green one is having this square markers. The orange one is having this circle markers, and the blue one is having the star markers. Now, if I print this entire plot in a using a grayscale printer, so black and white printer essentially, the plots will be still understandable by somebody, right? Somebody reading through this. But this is not looking really good because you can see that we have kind of clobbered everything together, right? So what if I want to change the shape of the plot? Maybe I want the plot to be bigger in the horizontal dimension, right? Maybe slightly longer like that, right? Maybe I want that. So for that, before creating the plot, I have to create a figure. Then I have to create a plot. So I would say plt.figure. Nothing will happen. Nothing will happen. Just keep this in mind. If I say plt.figure, what we have essentially done, before creating a plot, we have created a figure. Essentially, figure is kind of a container for containing those plots. So these plots are going into the figure. Now, since you have contained everything into a figure, okay, what you can do, you can change the shape and size of the figure. Okay. So again, this is the function call again. Okay. So now we can pass in a certain argument called fig size, and we can pass in a tuple saying, okay, this is the size of the figure I want. Maybe I want this figure to take 3 rows and maybe 7 columns. Let's see what happens. Okay, that was wrong. I mean 7 columns and 3 rows. All right. So now see, the height of the plot reduced and the width has increased. Maybe I want to increase the width a little bit further. Maybe I want this to be 10. See? Now much better, I think. Again, data representation is pretty important for engineering. All right. So there is one very important thing missing in this plot. Okay. So we have given this an axis. We have given the axis proper names. We have proper labels. We have proper grids. But we don't have a proper title for the plot, right? What does the plot mean? I mean, what is this really? Okay. So for that, we use plt.title. And what is the title? We would say, for example, 3-phase sine waves. And now if I run this, let's see, it says 3-phase sine waves. And here there is an annoying output because we are using Jupyter Notebook. In pure Python, this does not happen. So what I just do personally, I put a semicolon after the last line if I'm plotting in Jupyter Notebook or in Google Colab. I just put a semicolon. So that annoying output to be suppressed. So now we have a 3-phase sine wave. So by default, now we have a plot title here. Now we have a proper axis labels. Now we have proper legends. Now we have made the plot in a manner that is suitable for printing in grayscale. So you can print them easily, right? So now that is kind of teaching you the philosophy of plotting, for example, right? You have to make sure that it is accessible. Accessibility is pretty important in any kind of technology, right? Your technology should be accessible, right? If you are plotting something, yeah, this is kind of a complete one, right? And again, as engineers, so whenever you are submitting lab reports, for example, as students rather, okay, make sure to follow these things, right? Make sure to plot the figures in a way that's immediately understandable what it is looking for, right? What you're looking for. For example, you are learning how induction machines work, right? Maybe this would be sleep and this would be torque, for example. So in the horizontal axis you have sleep, here you have torque, something like that. So now of course you would write sleep here, then on the vertical axis you would write torque here, and then on the whole plot write sleep versus torque, or torque versus sleep, whatever you want to say. Okay, so by default everyone knows that okay, I'm looking at this one. Okay, so this must be there, and also of course you have to put the proper axis values here, right? You have to, on a graph paper, you have to write down proper values here on the axis. So labeling is pretty important, right? Unless you do put proper labels here, your graph can be misrepresented, and sometimes it is done intentionally. And nowadays I'm seeing such things quite often, more often than I should expect to see. All right, with that said, let's jump into something important here. Maybe this is fine and all, maybe that's fine, because we have 3 plots that share the same time axis, right? I said I did plot them on the superimpose them because they share the same axis, right? They have the same independent axis, which is time. Now what if my plots do not share the same independent axis? Maybe I am plotting two different things, but I want to show them all at the same time, right? All at the same figure rather. What if I want to do that? So under those scenarios, what I would probably want to do, I want to create something called subplots. Okay, what I would want to create, I would want to create subplots. Now let me show you how we actually do subplots. Now for that, I would take a very simple example, and an example of simple functions like this. Simple functions. Say I want to create a subplot, but see what I want to show you here. Maybe, so let's take time, for example, t equal to n. So np dot sine, sorry, np dot linspace. Now my time is varying from 0. So let's call this t1 instead, because I will be doing 2 plots, but they won't be sharing any of the axes. Okay, they would be different kind of plots, but maybe they want to convey the same ideas. Okay, so let's say, let me show you, it will be understandable. Let me show you something like this. So 0.5. So my linear space starting from 0.5 going up to minus 0.5 to 0.5, and let's say I want to take 10,000 points. 10,000 points. Okay, and I want to plot something. This is a signal again. Okay, and say for that, maybe I want something like this. Maybe I want to plot one. So what I'm plotting is LC. So it's a signal basically. So sine of 1 by t, right? Again, t1 is just a name of the variable. Okay, I want something else. Maybe I want to plot, I want to have another axis, t equal to say np dot linspace, say minus for example from minus 10 to plus 10, and again 1,000 points. Again, number of points are also different. So I'm starting from minus 10 to plus 10, and I'm taking 1,000 points, and maybe x2 would be np dot tangent tan t2. All right, nice. Now I want to plot them. Of course, they're not sharing the same time axis. They do not have a shared axis. So I would probably, if I am like educated enough, I won't plot them on a single plot, right? I won't superimpose them because they're not sharing the same axis. I mean, if any of the axes is shared, maybe time, maybe amplitude, something like that, then I can plot them. Perceivably, I can plot them on a single figure, right? A single plot. Right? But I'm not going to do that. Instead, what I want to do, I want to create a single figure, and maybe I want to plot them side by side. Okay, one after another, side by side. So essentially, if you think about it, I want to make 2 different plots side by side, right? One after another, right? One plot here, and right next to it, another plot. So one plot here, right next to it, another plot. Maybe I want something like that, right? So think about it as an array. Okay, as an array. So essentially, I want to create an array of 2 plots. Okay, and You will see what I mean shortly. So before we start even, let's create a figure. So plt dot figure, and let's create a fixed size of say 10, maybe not 10, maybe 7 comma 4. So we have 7 units of length in this axis and 3 units of length in this axis, right? So we have created a figure. Okay. Now instead of saying instead of plotting them naively, I would say plt dot subplot. Now inside this figure, what we are doing now, we are creating subplots. So subplots are essentially doing multiple plots, okay, inside the same figure, not superimposing them. So now how many rows do I want? So right now what I want my plots to be one after another horizontally. So essentially I would create one row of plots. So one plot and then another plot right next to it. So one plot, another plot right next to it. So I would want one row and 2 columns. Basically on the first column I would have one plot, and the next column I would have another plot, but essentially it's a row of plots, right? So I would want one row, okay, but 2 columns. And right now I'm looking at the first figure of that. And now if I say plot, sorry, plt.plot, plt.plot, and say for example I say t1 comma x1, okay, and then I'm saying this, say plt dot subplot 1 comma 2 comma 2. So this is the same subplot configuration, but I'm looking at the second plot. So essentially the second element of the plot array. So plt dot plot once again, and this would be t2 comma x2. Okay, so this is the entire figure configuration. So we have created a figure, okay, and then we have created 2 subplots, and then we have plotted 2 different things. Let's run these. See, we now have 2 different plots right next to one another. Maybe the width is not that much. Maybe I want to increase the width. Maybe I want to make it 10. Nice. And again, this tan wave is pretty annoying because I have to modify the axis for the tan signal, for example. Let's instead make this an exponential. Will be fantastic. Right, exponential. Now here we have 2 signals for which the Fourier transform do not exist. Okay, just to show you examples. So here we have 2 signals for which the Fourier transform. So this signal does not have a Fourier transform because it is violating one of the Dirichlet conditions. What is happening is within these limits there are infinitely many maxima and minima. So if you take these limits, the signal oscillates so fast that there are infinitely many maxima and minima. So this signal won't satisfy the Dirichlet condition, and it won't have a Fourier transform representation. And this is unbounded, very simple. So I'm kind of showing I'm kind of serving a purpose by plotting them on a same figure, but they do not go hand by hand on a same plot, right? I cannot just plot them on top of each other, right? Because they are not the same, but they kind of convey the same message. So I'm showing you examples where the signals do not have Fourier transform. So now we have a subtitle, plt dot subtitle. Subtitle means it's a super title, for example, right? So say signals that do not have Fourier transform for different reasons, of course. And of course I say that whenever I'm doing it on Jupyter notebook and things like that, I do like it. So now I'm showing you signals that do not have Fourier transforms, but for 2 very different reasons. This one has infinitely many maxima and minima within any small bounds about the origin, and this is strictly unbounded. So they do not have Fourier transforms. Rather, I would say examples. Just as an example, because you people are also learning Laplace transform, this signal does not even have a Laplace transform also, but this one has a Laplace transform, of course. So none of these have Fourier transforms, but yeah, very different things we're discussing. All right. So now independently, I can label each axis. For example, for this subplot, for the first subplot, of course, I would say, for example, plt dot x label, x label. Say I would say time, of course, in seconds, and plt dot y label, I would say amplitude. And let's copy these for the second plot as well, because they would have so these two plots essentially, since they're independent plots, I would have independent axis labels like that. So if I do the plot, yeah, like that. So now again, since I'm zooming in and the size of the figure is not really good in that case, so what is happening, they're kind of superimposing on another. Let's make this 12. Yeah, see examples of signals that do not have Fourier transforms. So yeah, so these plots are serving a certain purpose, and again we have proper labels in the axis and everything. So this is known as a subplot. Okay, right? Now we are not just limited to subplots of so we have just created a one row of subplots, right? What if I wanted to do the subplots, right, one after another? So one should be on top, the other should be on the bottom. What if I wanted something like that? I could have done that easily. So here, when I created the subplots, I created one row of plots and two columns of plots. See, this is one row of plot and two columns. This is the first column and this is the second column. So what if I just modified this and instead said this is 2, 1. So then I would have two rows and one column. Then I would have to also say 2, 1. And here, if I do the plot here now, see, now it has a different representation. So because these two plots have been now, instead of being side by side, now they're on top and bottom like that. Again, we have to now modify the size of the plot. But the point again stands. The thing is, it's entirely up to us how we want to represent our data, right? Good. So with this sample, let's go back. Let's create two more signals. Okay. Right off the top of my head, I can figure out another two signals where these things do happen. So np dot. Okay, maybe this example is enough already. So I would jump into something else. So the point being, you can also create arrays of three any dimension and make a subplot like that. Okay, it could be 2, 2. Maybe let's do that instead. So it won't be a wastage of time. So we have created an exponential wave. Let's create a negative exponential linspace. The same axis, same thing. We are using this array. The x3 np.exp. That's also does not have a Fourier transform. So, and say t4. Let's say from -5 to, for example, 10, and I'm taking 1,000 points here, and say I'm saying x4 equal to np dot do I have Heaviside theta? Yeah, we have Heaviside theta. We have Heaviside theta function, which is essentially the unit step function, t4, and let's multiply this with t4. So what I essentially have is t multiplied by Heaviside theta t, so tut, which is the ramp function, unity ramp function, right? So none of these have Fourier transforms, proper Fourier transforms. So now if I want to plot them, I would need to make the plot slightly bigger in the vertical dimension, so I'd make them 8, maybe 9 instead. Okay, and now I have 2 rows and 2 columns for my plot. Okay, so 2 rows and 2 columns, 2 rows and 2 columns, right? So now look carefully. I have 2 comma 2, which indicates there are 2 rows and 2 columns, and this was the first plot, this was the second plot. Now I want 2 more plots. So what can I do? I can just copy paste. So same subplot configuration. Now this would be the third one, and of course I have created my own arrays for those. Okay. And this would be the fourth one. Here are the arrays. Now what if I plot these? Say something is okay, heaviside function is showing me an error. What is the problem, bhai? Okay, let me see. What is the problem? Okay. I told you that there is an ambiguity of heaviside theta function. Somebody says at t equal to 0 we have a point. Okay, got it. Fine, no problem. Let's say at t equal to 0 we have a value of 0. I will be fine with it. Alright. Right. So now look at 4 plots. I might want to zoom out a little bit. Just hold on for a moment. So now I have 4 plots depicting 4 different signals that do not have Fourier transforms. But again, the point stands here is that I'm making subplots instead of superimposing them, because they have different axes. They do not go together, right? But they share a common purpose, right? What purpose? Making sure that Fourier transform fails. Anyway, that's the point. So you can make subplots like that. Okay, these are subplots. And again, all the techniques that you have seen so far, like legends and everything, you can do that as well here. And inside a subplot, you can, rather I would say, you can superimpose other plots. So the point being, you can superimpose other plots inside a subplot. Maybe here I want to plot another thing, something else. Here, along with this one, I want to superimpose something. So each subplot individually is the plot. So I can superimpose something here. Maybe I want a T4 along with that. Of course, the axis should match here. And on that, maybe I want another ramp function that has double the slope. So T2 into x4. Again, if you have forgotten signals and systems, don't worry. The point being, individual plots here are proper fully fledged plots themselves. So all the other techniques that you have seen, like grids and everything and legends, everything, those will apply to individual plots. But everything is encapsulated inside a single figure, and that is how you actually represent these data. I think you people got this already. All right, so let's go to the next. Hold on for a second. All right, so it has been 1 hour 30 minutes already. So far what we have seen, we have only used line plots actually, really, right? So there are several other kinds of plots, many different kinds of plots. Okay, let's see a few of them. Okay, let's see a few of them. Let's pull random data. Okay, it will be useful. Let's create an array x of np dot random dot rand, and say let's pull 1000 points random data. Nice. Okay, and say plt dot, let's say okay. So what I'm doing right now is I'm plotting a histogram. Let's see. So essentially what I have is a histogram. I mean, it's not really that fantastic here, but look very carefully. It is showing you that from 0 to 1, the distribution of numbers. So about 100, and so within these limits, for example, between, say for example, 0.9 and 1, we have about 120 points like that. Between 8 and 0.8 and 0.9, I have around 90 points like that. So it is showing you a distribution of these. It would look even better if I, instead of doing this, instead of pulling the random numbers from a uniform distribution, if I pull them from a normal distribution, so random, right? So I am pulling 1000 points from a standard normal distribution. Standard normal distribution means a normal distribution where the mean is 0 and the standard deviation is 1. So now see, this is kind of looking like a bell curve, but we have only taken 1000 points, so there is margin for error, right? So what if I take 10,000 points? Okay, so now what happens? This is kind of showing you a better one, right? Now whenever I am plotting histograms, we have a parameter called number of bins. So again, those who have studied statistics, you know that bins are essentially the spacings between the independent axes that we are assuming here. So maybe instead of saying by default number of bins would be, say, maybe 50, it will be a much smoother. But hold on. Oh, n bin. Oh, just bins, right? So bins would be, say, 50. See, now this is kind of looking like a normal distribution, right? So hopefully it's normal distribution, proper normal distribution, right? Nice. So that's your histogram plot, right? So another kind of plot you have just seen, histogram plot, for example. Nice. All right. So again, you can combine different plots like that. Again, this is again a fully fledged plot, and you can actually do whatever you want with this kind of plots, right? And if you have any query, feel free to ask. All right. Okay. So I would want to plot something slightly more interesting here. I want to make a plot called a polar plot, maybe. Okay, let's say a polar plot would be pretty interesting. Say again, let me create a time axis. Okay, time axis, for example. Let's not say a time axis. Say on polar plot you have theta and r. Let's say a theta axis, and say np dot linspace. Say I'm starting from 0 and going up to 110, maybe going up to 20 with the points. And then you have r, again from the polar plot convention here. So let's say r equal to theta, and I want to plot them. If I just say plt dot plot and theta comma r, okay, it will be just a straight line, right? Not very interesting, right? What if I want to make the plot in polar coordinates instead of these being in Cartesian coordinates? If I want to make this plot in polar coordinates, so I say, okay, instead of saying, I say projection. Okay, maybe I have forgotten how to create polar plots. Okay, so with that, if I forget that, what I can do, I can easily go to this. What do I see? I want to look for polar plots. Okay, let's go back here. Just a moment, huh? Okay, I have nice looking polar plot, fine. And how do I call polar plot functions? Okay, I have this line that I need to put whenever I want a polar plot. So let's write that down. So this is how we people handle our engineering, right? So let's write that. you don't have to worry about how we actually use this. So this is creating subplots and returning some axis objects. Okay, you just have to, instead of saying plt dot plot, you have to say ax dot plot. Okay, and theta are common. Right, now let's plot this. Now we are creating a polar axis and plotting them. See? So what is this? Now this is an Archimedean spiral. Those who know, this is an Archimedean spiral, right? So r equal to theta is the function for Archimedean spiral. Nice, right? That is what I said. That is why I said that the Matplotlib documentation is gallery is pretty important here, right? Okay, good. Let's make a 3D plot, for example. Okay, well, let me show you a few more demos, right? Would be kind of more useful in that context here. Okay, let me show you a few more demos, right? So save that, pull spider from my computer. Okay, so these imports have already been done. Let me just copy paste something from something what I did earlier. Okay, now important point to note here is that what we are doing, what kind of plot we are making is something called a contour plot. Okay, a special kind of contour plot. And okay, let's see. And here what we are doing is, let me show you. Okay, so is it visible properly? Let me increase the figure size. PLT. Not sure if this will work. Okay, this did not work here. Okay, unfortunately, if I zoom this figure in, unfortunately, you don't get to see what's happening here. But let's see. So I particularly made this plot when I was teaching electromagnetic field theory. Okay, to represent vector fields, for example. Okay, to represent vector fields. So let me show you a pretty simple example. Right, let me show you a pretty simple example. Say, all right, so let me just insert say this x. Okay, look at a vector field, for example. So imagine it's like a flow. Okay, and maybe it's not an electric field again. Okay, someone is saying, what if I explain the? I will explain the polar plot once more. Look at this vector field, for example. Okay, so what is happening is, I mean, if you imagine this as a fluid flowing, something like that, then what is happening? From here, somewhere from here, fluids are being generated, and then the fluid is flowing out. So as a whole, if you take this entire picture as a whole, there is a total outbound flow. So this is kind of representative of a vector field where the divergence is positive. Okay, there is a positive divergence. There is a total outbound flow out of this. So divergence is positive. Okay, this is an example of something like that. Now what if I have something like this? Okay, now again the same idea. Maybe imagine something like this. From this point flow is being generated. Okay, it could be electric field or something like that, and the flow is going out. Again there is a net outbound flow. So again this is representative of a field where divergence is positive. Okay, I'm just making simple changes here. Okay, this is again, these are the things that I make for teaching people. Okay, now look at this one. Look at this one. Okay, see something like flows somehow. Imagine that. Look at this one. Some flows are coming in from the right hand side and from the left hand side, and whatever amount of flow is coming in from the right hand side and left hand side are basically being transferred from the top and the bottom. So if you take this whole figure as a then it is a zero divergence field. So why zero divergence field? Because the amount of flow that is coming in is the amount of flow that is going out. Okay, so it's a zero divergence field, for example. Okay, look at this one. Again, this is Python for engineers, right? Look at this one. So it is something like flow is somehow accumulating from everywhere inside this box. So if you take this box as a whole, then it would be a negative divergence field. Okay, negative divergence field, something like that. And say maybe I want this. No. Hold on. All right, now look at this one. Now of course the divergence of this field is zero, because again the total amount of flow that is going out is equal to the total amount of flow that is going in. But look at a very small region of this one, right? So imagine if you release something here, if you release an object, so imagine this is representative of a fluid flowing, right? And imagine you releasing an object that can float on water, right? So maybe this is water flowing, right? If you release an object like that, then what will happen? The object will rotate like that, right? Keep on rotating. It won't go outside your box here like that. So the divergence of this field is zero. So there is no net flow from no net flow going outside, or net inbound flow, or no zero net outbound flow. So but there is a certain rotation in the field. So this field is rotational, and because of that this field has a certain value, non-zero value of curl, right? So this is a representative of a field which is rotational but does not have any divergence. So zero divergence field but rotational field. Okay, and this kind of fields can never be created with an electrostatic system. Okay, rotational fields, for example. So an object will automatically rotate in this field. So you can understand that using very simple plots we can show so many things in Python. Again, someone was asking, okay, how what is this, what does this mean? So essentially what happens is that we have two axes here. What axis? We have one axis called r and one axis called theta. And in polar coordinates what you essentially have is that you measure the theta axis. Okay, you measure the theta axis. So essentially look at the degrees here. So you start measuring from this angle. Okay, so for a certain value of theta, what is the value of r? Okay, that is what. So theta is independent. So for certain value of theta, what is the value of r? Okay, so theta is independent, right? So essentially when theta is 0, r is also 0 in this plot. Now as theta is increasing, what is happening? R is also increasing, because in this plot r is equal to theta, right? But theta can become 360 degrees, but when theta becomes 360 degrees, it's essentially 0 once again. But when theta is 360 degrees, essentially 2 pi, r has a value of 2 pi, right? So r has increased, but theta has become 0 once again. But again, theta is going back, and now theta has become 2 pi. Okay, it's essentially equivalent to 0, but the r has a value of 4 pi now. So r is gradually increasing, but theta is going back to 0 again and again and again. So essentially this is creating something called a spiral. Okay, so polar plots are pretty important when we have an angular axis like that. Okay, when we want to plot things in polar coordinates per se. Okay, so again this is an example of a vector field. All right, very simple, I think. Now since we are talking about these kind of things, Python also supports doing image processing, right? And for that you might want to plot images. You might want to plot images for example, for that, right? So if you want to plot images are essentially two-dimensional arrays, for example. And instead of just importing an image like that, let's instead bring an image here. I'm using a Python library called scikit-image, and from that I'm using the data library. So see, look at this. So from image, so this scikit-image, import data. So scikit-image data library, I'm importing something. I shall be importing something. Okay, and same x is my this is my image. Data dot Chelsea. Nice. So from data I am importing Chelsea. Fine. What is Chelsea? Okay, so my image. Now if I print this, what happens is all I see is an array. It's a two-dimensional array. Okay, nice. NumPy array. But if I want to plot this, it will be pretty hectic and pretty useless because it's a three-dimensional array, right? And it will be pretty useless. So I can say image.shape, my image.shape. Again, it's a NumPy array, so I will get to see the shape. So it's a 300 by 451 by 3 array. So it's like a two-dimensional array, but it has 3 of them. Okay, one after another. So now what I can do instead, instead of plotting them as an array, I can plot this as an image. But I can say plt.imshow. So it says image show. And if I do this, what I now have, that image. So now it's actually plotting an image, right? Plotting an image, right? Let me show you a very simple arithmetic that you can do on this one and generate something pretty interesting to some extent, right? Let's create an array that is equivalent in size of my image. Okay, so now this is my array. Let's create an array that's equivalent in size to my image. So my array would be np, and now there is a NumPy function called once like. So once like, and so it will, let me show you what my image. So what happens here is that NumPy is taking my image. This is an array. It has certain dimension, it has certain data type, and it is creating another array for me which will only contain 1 everywhere. It will contain 1 everywhere. Okay, but the shape and size and everything would be identical to this images array. So essentially what I have done, I have created a white image. I have created an image of a particular color. You will see. So with that, if I multiply this, for example, say for example with 100. So what essentially I did, I created an image where every pixel has a intensity value of 100. Again, pixels are essentially 3 colors: red, green, and blue. Okay, and every pixel, every red pixel essentially has a value between 0 and 255. It's an 8-bit value. So 0 means complete darkness, so black, and 255 means complete light, so essentially white. Okay, and anything in between would be essentially a different color, for example. So I have essentially created a grayscale image. plt.imshow, say my array. So essentially it's a value of gray, right? Something like that in between, right? Some sort of a gray, right? But I don't want that, so I say I would create a white image. So this would be a completely white image. Okay, let me just show you that. Uh, let me just show you that. So it's a complete white image. So all the pixels are 255. So all the pixels are bright. So this is a white image. Maybe it might look like there is nothing, but this is a white image. Okay, and maybe say I want to create another plot where I would subtract the image of this cat from this white image. Okay, so I would say my array minus my image. So this was the this was the image of the cat, and I am subtracting it from the white image. Okay, and let's show the image. We have done simple arithmetic, right? Simple arithmetic. Now what have I done? So essentially this is the negative of the image. This is essentially the negative of the image. Nice. Right. And in case you are interested, you can go to my GitHub page there. Let me show you. Okay, you can go to my GitHub page and open this pie image. So I created a big tutorial of image processing using Python. Okay, and go to this link. You would see that. Okay, click this one, image processing in Python, for example. So it pretty much gives you an undergraduate course on image processing with Python. Okay, all right. So let me just show you what different things. For example, this is a color image, and these are the different channels. So I chose this color image, and this is a Macau. And look very carefully. This has particular red portions, green portions here, and blue portions here. So if I just highlight the red portions, those are things. If I highlight the green portions, and okay, something like that. So this is a complete random. So this is what random values look like if I plot them as an image. So this is what random numbers look like if I plot them as an image. So this is the grayscale version. This would be a color version. Okay, and these are the image histogram. Some of you might know. So this is, for example, how intensities, how many pixels there are of different intensities. For example, this is a very low contrast image. What we can do using simple numpy here, we can stretch the contrast, and this is a high contrast image. So from this image we have made this one. So this is the high contrast image. Nowadays on mobile phones you just click autocorrect and automatically it autocorrects, but this is actually. So let me just give you the link of this. So again, I'm posting the link on the live chat somewhere. Okay, some simple. So again, this is an inversion. So this is an inverted image. Okay, these are gamma correction. Some of you might already know what gamma correction is. If you don't worry. Okay, these are something called segmentation. You don't worry about that. These are noise removal. So you look at this image. This is pretty noisy. Okay, now significant amount of the noise has been removed. Again, this is pretty noisy. With another kind of filtering, we have gotten rid of a lot of noise. Again, this is an image, and we have used two particular filters. And what are filters? They are essentially signals that we convolve the original signal with. So essentially this is a signal. It's a 2D signal. Instead of being a one-dimensional signal, image is a 2D signal or a 3D signal, right? And we are essentially doing convolution. Okay, and we are doing convolution with certain filters. What are filters? Filters are essentially systems, right? So systems with the impulse response. So you know the impulse response of the filter. Okay, and essentially we will pass that, and accordingly we shall have this one. So this is a noisy image, and of course this is after removal of the noise, for example. And there are several other things. So for example, look at this image. We have detected only the edges. Okay, and look at this one. We have only detected the edges here, only detected the vertical edges, horizontal edges. And this is something that we achieve by just doing convolutions, very simple convolutions with very simple systems where we know the impulse response of, right? So those act as filters. Okay, and again, this is the image of the moon. I don't know how it will appear on YouTube here again, but this is again a sharpened version of the image. Okay, this is a sharpened version of the image. This is a sharpened. So see, this is a bloody image, but again, look at this one. All the creases are pretty properly visible. So this is a sharpened version of the image. All right. So there are, and again, I wrote all these mathematics here. Okay. Again, this is a kind of a bloody image, and this is a sharpened version. And this is the Fourier transform of the image. What it means, you don't really, I cannot really tell you right now. Yeah. You can do that as well. Okay, you can blur an image. That's an easy thing. Okay, so again, these are very simple things, I would say. Okay, but this is kind of a fundamental course on that. Right. All right. And of course, this Python library would allow you to do quite a few processing. So all in all, you can understand that there are several types of plots that you can generate, several things that you can do here. Okay, several interactive plots you can generate. Okay, several interactive plots that you can generate, and I have shown you several. This kid is shouting. Hold on for a second. Okay, anyway, so you can have different. And also, just let me show you on one plot here, just to show you a certain thing. So again, let's see a simple example. So again, this is a plot which is animated. I'm not doing anything. Okay, this is a plot which is animated. Animated plot. Okay, this is called Conway's Game of Life, named after John Conway. All right. Nice. All right, so that would be the end of today's discussion, and there are several other kinds of plots which I cannot really go into today. And did I miss anything? I don't think I missed anything yet. We talked about legends and everything. We talked about how we create plots and settle them. All right, and oh, there is one thing I missed. Let me create a new notebook. How do I create a new notebook here? Yeah. But do I have to open Colab once again? Just one more thing, huh? Before we end. Let's create a new notebook. Okay, and this you must know, in my opinion. Okay, so what happens is, the very first thing that we did today was that we imported NumPy and Matplotlib, right? And we wrote np everywhere. And this is so common that we have a magic function. Okay, we have a magic function. So we say percentage pylab. So instead of doing all those imports, we say percentage pylab inline. So that's called a magic function. And it says populating interactive namespace from NumPy and Matplotlib. Now I do not have to say np.plt.plt. Things like that. I can just say t equal to linspace 0, 10, 1000, x equal to sine t, and plot them. Plot t comma x. That would do. Again, this is for interactive exploration. So if you are just in a hurry and you want to interactively explore a few things, I would recommend you to pylab inline and just go your merry way. So it pretty much takes away all the hassles. Okay, dot and all those things. Everything will work again. So x label X label, and you would have, say for example, time, okay, in seconds. And then we have Y label, and you have amplitude. Just to show you that everything works really. Same thing, right? So you can just, instead of importing NumPy and Matplotlib, those imports are so common that instead you have a single import like %pylab inline. Okay, just keep that in mind. All right. So thank you very much for being here for so long, and we're going to end the discussion right now. Again, if you have any query later on, I would suggest you ask me, or rather drop me an email. Fine, fantastic. And we are going to end our discussion here today on Matplotlib. And on the next one, we shall look at some parts of SciPy. So we are going to learn how to solve differential equations in using NumPy. Okay, how to do integrations numerically, how to do differentiations numerically, some sort of numerical computations we shall learn on the next class. All right. Thank you. See you tomorrow with control systems.